All right, learner, welcome to another deep dive.
Yeah, welcome back.
You know you're here because you want to know stuff,
Actually,
but you want to know, right, you don't want to just have like a surface level understanding of something.
exactly. And you don't want to wade through like piles and piles of textbooks.
Exactly. You want it efficiently. You want it like,
Contained.
yeah, contained. And that's what we aim to do here.
Absolutely.
Today, we're looking at direction cosines and direction ratios.
Yes.
And this is like, three-dimensional geometry.
Yeah, it's like the bedrock, really, of how we understand lines and planes in space.
Right. And so we've got a textbook here. It's a math textbook.
Yeah, Class X, like high school level math.
Right. And they really dive deep into this stuff, but they do a good job of like explaining it and making it pretty clear.
Yeah, and they use vector algebra, which I think is a really elegant way to approach it.
Yeah.
Like it just simplifies a lot of the concepts.
And, there was this quote in the beginning of the book by Ada Morgan, I think it was. He said something like, "The moving power of mathematical invention is not reasoning, but imagination."
Oh, yeah.
And it kind of struck me as like profound because I think people think of math as like very rigid, very like logic based.
Yeah, but really to make these leaps, you need to be able to like visualize things in your head.
Exactly.
And that's what these concepts help us do.
Exactly. So that's our mission today.
All right, let's do it.
All right. So like, what are these things? Direction cosines? What are they all about?
So think about a line,
Okay.
like just a straight line in space.
Like in 3 dimensions.
Yeah, exactly, 3 dimensions.
Oh, okay.
And it's directed, which means it has an arrow.
Okay. So it's got like a direction it's going.
Yeah, it's not just a line. It's like a path.
Okay. Got
And
it.
that line makes angles with the X, Y, and Z axis.
Okay.
We'll call them alpha, beta, and gamma.
Right.
So the direction cosines are literally just the cosines of those angles,
Okay.
like cos alpha, cos beta, cos gamma.
So we just take the cosine of each angle.
Exactly. And usually we label them L, M, and N just for shorthand.
Okay. But like, why is it important that it's a directed line?
Well, imagine flipping the arrow on that line.
Okay.
Now the angles change, right? They become their supplement.
So like alpha becomes 180 minus alpha or pi minus alpha.
Exactly. And the cosine of a supplementary angle is just the negative of the original cosine.
Right. So if you flip the direction, the signs of the direction cosines flip.
Exactly. So any line actually has 2 sets of direction cosines, depending on which way you're pointing it.
Okay. So we need to be clear about the direction to get a unique set.
Exactly.
Got it.
And what if the line doesn't pass through the origin?
Right. Because like most lines don't just conveniently go through 0, 0, 0.
Yeah, that's a good point. Well, there's a trick.
Okay.
You just draw a parallel line through the origin.
Oh, okay.
Because parallel lines have the same direction.
Yeah. They're like a point the same way.
Exactly. So they'll have the same direction cosines.
So by shifting it to the origin, it makes things easier to work with.
Exactly.
Okay, so now there's this equation that comes up a lot. L squared plus m squared plus n squared equals 1.
Oh, yeah, that's like the fundamental relationship for direction cosines.
Right, but like where does that come from?
So picture a line going through the origin
Okay.
with direction cosines L, M, and N.
Mm-hmm.
Now, pick any point on that line. Call it P with coordinates X, Y, Z.
Okay.
Let's say the distance from the origin to P is R.
Okay, so OP equals R.
Exactly. Now think about dropping perpendiculars from P onto the X, Y, and Z axis.
Okay, so like projecting it onto each axis.
Exactly. And the lengths of those projections are LO or LNR and NR.
Wait, how do we get that?
Think about the definition of cosine in a right triangle.
Okay.
So the angle alpha that OP makes with the x-axis cos alpha is L, right?
Right.
But it's also the adjacent side, which is x, divided by the hypotenuse, which is R.
Oh, so L equals X over R, and therefore X equals LR.
Exactly. And you can do the same thing for beta and gamma to get y equals miss R and z equals NR.
Oh, I see. So it all comes back to those
Yeah.
right triangles formed by the projections.
Precisely.
Okay, so X equals LRY equals miss R, Z equals NR.
Got it. Now, if you square those equations and add them all up,
Okay.
you get x squared plus y squared plus z squared equals L squared R squared plus m squared R squared plus n squared R squared,
Okay.
which is the same as R squared times L squared plus m squared plus n squared.
Right, because you can factor out the R squared.
Exactly, but x squared plus y squared plus z squared,
Yeah.
that's just the distance squared from the origin to P.
Right, which is R squared.
So we have R squared equals R squared times L squared plus m squared plus n squared.
And if we divide both sides by R squared,
We're left with 1 equals L squared plus m squared plus n squared.
boom.
There it is.
It's a beautiful equation.
Yeah, it really ties it all together.
It shows that the direction cosines aren't just any random numbers. They're constrained by this relationship.
Right. So knowing 2 of them basically determines the third one.
Exactly.
Okay, so that's direction cosines.
No.
What about direction ratios? So direction ratios are basically any three numbers that are proportional to the direction cosines.
Okay, so if L, M, and N are the direction cosines, then the direction ratios are like A equals lambda LB equals lambda M and C equals lambda N.
Exactly, where lambda is just any non-zero number.
Okay, so they kind of capture the direction, but not the exact cosine values.
Yeah, it's like scaling the direction cosines by some factor.
And the book says some people call them direction numbers too.
Yeah, it's the same thing.
Okay, so can we go back from direction ratios to direction cosines?
Absolutely, there's a formula for that.
Okay.
So L is plus or minus A divided by the square root of a squared plus B squared plus C squared.
Okay.
And M and N are the same, just with B and C instead of A.
So we divide each direction ratio by that square root thing.
Yeah, and that square root is basically the magnitude of a vector with components A, B, and C.
Right, so it's like normalizing them.
Exactly. We're
Yeah.
scaling them so that they satisfy that L squared plus M squared plus N squared equals 1.
And what about that plus or minus signs?
That's because a line has two possible directions.
Right, so we choose the plus or minus depending on which direction we're interested in.
Exactly. If you flip the direction, you flip the signs.
Okay, so direction cosines are unique. They define a specific direction, but direction ratios are not.
Right, but they both give you information about the orientation of the line.
And you can convert between them if you need to.
Exactly.
Okay, now what if we have a line that passes through 2 points?
Oh, yeah, that's a common scenario.
So how do we find the direction cosines in that case?
Well, the book has a really nice formula for that.
Okay.
So if the points are P with coordinates x, y1, z1, and Q with coordinates x2, y2, z2,
Okay.
then cos alpha is x2 minus x1 divided by PQ,
Okay.
where PQ is the distance between P and Q.
Right.
Similarly, cos beta is y2 minus y1 divided by PQ, and cos gamma is z2 minus z1 divided by PQ.
So we take the difference in coordinates and divide by the distance.
Exactly, and PQ is just the square root of x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared.
All right, the distance formula. So it's like we're finding the components of a vector pointing from P to Q.
And then normalizing it by dividing by the magnitude.
Okay, that makes sense.
And there's a note that says the direction ratios of the line segment joining P and Q can be taken as just the differences in coordinates.
So x2 minus x1, y2 minus y1, psi2 minus c1.
Or x1 minus x2, y1 minus y2, z minus c2.
Right, it doesn't matter which way you subtract as long as you're consistent.
Exactly, because it just flips the direction.
Okay, so we can easily find direction ratios from 2 points, and then we can use those to find the direction cosines.
Exactly.
Okay, now the book has some examples. Let's go through those.
Yeah, let's see how this works in practice.
Okay, so example 1 says a line makes angles of 90 degrees, 60 degrees, and 30 degrees with the x, y, and z axes.
Okay,
And we need to find the direction cosines.
so that's just a direct application of the definition.
Right. L equals cos 90 meter equals cos 60n equals cos 30.
Which gives us L equals 0, M equals 1/2, and N equals root 3 over 2.
Okay, easy enough.
Example 2 is a bit different. It gives us the direction ratios 2, minus 1, and minus 2.
And we need to find the direction cosines.
So we use that formula we talked about.
Right. L equals plus or minus a under the square root of a squared plus b squared plus c squared.
Exactly. So first we calculate that square root, which is the square root of 2 squared plus minus 1 squared plus minus 2 squared.
Which is 3.
So L is plus or minus 2 over 3. M is plus or minus 1 over 3. And N is plus or minus 2 over 3.
And the example chooses the positive signs. So
Yeah.
the direction cosines are 2/3 minus 1/3 and minus 2/3.
Exactly.
Okay, so we normalize the direction ratios to get the direction cosines.
Precisely.
Example 3 gives us 2 points, minus 2, 4 minus 5, and 1, 2, 3.
And we need to find the direction cosines of the line passing through those points.
So we use that 2-point formula.
Right. First, we calculate the distance between the points, which is the square root of 1 minus 2 squared plus 2 minus 4 squared plus 3 minus 5 squared.
Which simplifies to the square root of 77.
Then L is 3 over root 77. M is minus 2 over root 77. And N is 8 over root 77.
And the example confirms those values.
Perfect.
Okay. Example 4 is a bit conceptual. It asks for the direction cosines of the x, y, and z axes themselves.
So think about the x-axis.
Okay.
It makes an angle of 0 degrees with itself and 90 degrees with both the y and z axis.
Right.
So its direction cosines are cos 0, cos 90, cos 90.
Which are 1, 0, 0.
Exactly. And similarly, for the y-axis, it's 0, 1, 0, and for the z-axis, it's 0, 0, 1.
So they kind of align with the unit vectors along each axis.
Yeah, it makes sense intuitively.
Okay, and lastly, example 5 gives us 3 points. A 2, 3 minus 4, B, 1 minus 2, 3, and C, 3, 8 minus 11.
And we need to show that these points are collinear using direction ratios.
So collinear means they all lie on the same line.
Exactly.
So if we calculate the direction ratios of AB and BC, they should be proportional.
Right, so for AB, it's 1 minus 2 minus 2 minus 3, 3 minus minus 4.
Which gives us minus 1 minus 5, 7.
And for BC, it's 3 minus 1, 8, minus minus 2, minus 11, minus 3.
Which gives us 2, 10 minus 14.
And if you multiply the direction ratios of AB by minus 2, you get the direction ratios of BC.
Right, so they're proportional.
Exactly, which means AB and BC are parallel.
And since they share the point B,
They must all lie on the same line.
so A, B, and C are collinear.
Proven.
Wow. Okay, so we've seen how direction cosines and ratios work in different situations.
And how they relate to each other.
And how they're actually really useful for solving problems in three-dimensional geometry.
Absolutely, they're foundational concepts.
So learner, just to recap,
Yes.
direction cosines are the cosines of the angles a directed line makes with the axes.
And they're always related by that equation, L squared plus M squared plus N squared equals 1.
And direction ratios are proportional to the direction cosines.
You can find them from 2 points on a line.
And you can use them to check if points are collinear.
So you've learned a lot today.
You've gained a solid understanding of these concepts.
And that's going to be really helpful as you continue your journey in three-dimensional geometry.
Exactly.
Now for some food for thought.
Yes.
Think about how these ideas might extend to higher dimensions.
Oh, yeah, like 4 dimensions or 5 dimensions.
Exactly. How would you define direction in those spaces?
That's mind-blowing.
And what about different coordinate systems?
Right, like instead of X, Y, Z, what if we used polar coordinates or spherical coordinates?
Would the concepts of direction cosines and ratios still apply?
And where in the real world do these things matter?
Oh, in so many places.
Like navigation.
Yeah, GPS satellites use these concepts all the time.
And computer graphics.
Yeah, to render three-dimensional objects on a screen.
And robotics.
Yeah, to control the movement of robots in space.
So many applications.
It's fascinating.
Well, learner, we hope you enjoyed this deep dive.
Yeah, we hope you learned a lot.
And we hope you keep exploring.
Keep that curiosity alive.
And we'll see you next time. Yeah.
Until then.
Bye.